In the first part of this lesson, we discussed the disk method of measuring the volume generated by revolving an area around an axis. Now, the disk method will work only if that area that you revolve is in contact with the axis. Then only you will generate a disk. Now, what happens if an area is actually not in contact with the axis? Now, this is the axis that I'm holding, and this is the area. There is a space between them. Now, what kind of a solid is generated if I revolve this area now about this axis? Can you figure out? Now, when this revolution occurs, it is going to leave a big hole at the center. Is that right? So, we are not generating disk in this case, but we are generating a washer. Now, what is a washer? I'm sure you have seen washers used for fixing things. Now, here is an example of a washer. If you notice, there's a hole in the middle. Now, you have the graph of one function and the graph of a second function. There is an area enclosed by the graphs of two functions, and it is that area that we revolve about an axis, and it generates a washer. Now, in finding the area here, now remember, in the case of a disk, the area of one face is the area of the circle, which we said is pi r squared. Now, how about the area of this face of this washer? What we need to do is, we need to take that full disk, which has an area pi r squared, where r is the distance from the center to the edge of the outer circle. Now, from that, take away the area of the hole. If the area of the hole, if the radius of the hole is, say, lowercase r, and the radius of the whole disk is uppercase R, then pi r squared is the whole area, which is r is the uppercase R. Pi times uppercase R squared is the whole area, and pi times lowercase r squared is the area of the whole. So what you do is, you take away the area of the whole from the area of the complete disk. That will give you the area of the washer. In other words, pi times uppercase r squared minus pi times lowercase r squared. Alright, we're going to discuss that in this lesson. Alright, so we said when the area revolved is not in contact with the axis of revolution, we cannot generate disk. Now, let's take a look at one such example. Consider the area enclosed by the graphs of f of y equal to y squared and g of y equal to square root of y. They're functions of y. Alright? What is the graph of f of y equal to y squared? That is the graph of f of y equal to y squared. Remember, f of y equal to y squared is the same as x equal to y squared. And can you express that as a function of x? If x equal to y squared, then y equal to square root of x. That's the graph of this. So, this is the graph of x equal to y squared or y equal to square root of x. Alright. Now, this is the graph of x equal to square root of y. Now, can you imagine the area enclosed by this? That's the area enclosed by this, and we need to revolve this area, let's say, about the y-axis. Now, again remember, you can generate disk only if the area is in contact with the axis of revolution. Now, this is the way we generate a disk. But in this case, this area is not in contact with the disk. So what do? What kind of a solid will be generated by revolving this area about the y-axis? Can you visualize? If this area is revolved about the y-axis, what kind of solid will be generated? Well, let's approach this the same way as we did with the disk. Take a strip of area dA of width dy. Now, this is the area dA and the width of that is dy. And you notice that this area is not touching the axis of revolution. Now, revolving this area about the y-axis generate a, is that correct to say, generates a disk of width dy? Yes, it generates a disk with a hole at the center. Now, I want you to picture this. Take this area and revolve it about the y-axis. Now, let's see if I can find one of the things that... Alright, now here is that area and I need to revolve it about the y-axis. You see that there is a space there. So if you revolve this about the y-axis, it is going to be like this, which means it is going to leave a hole at the center, and therefore it is going to generate a washer. That's right. So it will be something like this. This is the washer. So look at that again. That small area dA, when revolved about the y-axis, generates this washer. And the thickness of the washer is actually the width of that area, which is dy. So we call this a washer. Now, the outer radius of this washer, what is the outer radius of the washer? What is the meaning of the outer radius? The distance from the axis of revolution to the edge of that washer. That is the outer radius. And we're going to call it uppercase R of y, equal to g of y minus 0. You see, this is g of y. And the distance of this graph from the y-axis, all of that is actually g of y. That means this whole distance is the outer radius. I hope you understand that. Pay special attention to that. Now, when this whole area is revolved, the outer radius is this distance, isn't it? And that distance is g of y minus 0. 0 is x equal to 0. So, r of y equal to g of y minus 0, which is actually g of y. Alright, so there you have, this is the outer radius, and that is r of y equal to gy. Now, what is the inner radius? Inner radius is the radius of this hole. The radius of the hole is this. And what is that distance? This is the graph of the function f of y. And therefore the distance of that graph from the y-axis is f of y. So the lowercase r of y is f of y minus 0, which is f of y, and that is this distance. So you must understand and distinguish these two radii. A washer has an outer radius and an inner radius. In this case, the outer radius is g of y and the inner radius is f of y. The outer radius is represented by the uppercase r. The inner radius is the lowercase r. And now, what is the volume of that washer when you revolve it about the y-axis? What is dV, the volume of that washer? Now, let me show you the disk that I used. If you look at this disk, you can see this is a washer, isn't it? Yes, you can see the hole there. Now, what is the volume of this disc, of this washer? Well, if you take the complete volume of the disc, including the hole, and then subtract the volume of the hole, is that right? In other words, the complete volume will be pi big R squared times the width, and then subtract pi small r squared times the width. And that will give you the volume of the washer. So, volume of the complete disc. The complete disc means the solid and including the hole. What is the volume of the complete disc? Pi times uppercase R squared dy. Now, that will give you the complete volume of the disc. Now, take away the volume of the washer, of the hole. What is the volume of the hole? The volume of the hole is pi times lowercase r squared times dy. dy is the thickness of the disc. So, the volume is the face area multiplied by the thickness. For the entire disc, the face area is pi times uppercase r squared and multiplied by dy. So the volume of the complete disc is pi uppercase r squared dy. The volume of the hole is pi lowercase r squared dy. Therefore, what is dV, the volume of the washer? The volume of the washer is the volume of the complete disc minus the volume of the hole. That will be pi times uppercase r squared dy minus pi times lowercase r squared dy. And you can factor out pi, and so dV equal to pi times uppercase r squared minus lowercase r squared times dy. Alright, if you notice there is a small error in here, can you spot that? That square must be for this radius. That's right. And this dy is going to be multiplying the whole of the quantity. That's very important. This dy multiplies the whole of this. In other words, pi times r squared minus r squared, uppercase r squared minus lowercase r squared in a parenthesis, times dy. Okay. Now, in order to find the complete volume generated by revolving this whole area, we integrate the dV. We integrate dV from y equal to c to y equal to d. So this is y equal to c and that is y equal to d. Is that right? That's the limit. So this whole area, when revolved about the y-axis, generates a volume V, and that is obtained by integrating dV from y equal to c to y equal to d. And how do we obtain C and D? C and D can be obtained by setting f of y equal to g of y. Let's do that in this case. What are the points of intersection? The points of intersection occurs where f of y equal to g of y or y squared equal to square root of y. And that happens at y equal to 0 and y equal to 1. So this is one point of intersection and that is the other point of intersection. So your value of C is 0 and the value of D is 1. And so V equal to pi times integral 0 to 1 uppercase r squared minus lowercase r squared dy. Now remember, our uppercase r is g of y and our lowercase r is f of y. So let's replace that. That would be pi times integral 0 to 1 square root of y, this is square root of y, all squared, minus, this is f of y equal to y squared all squared dy. Well, you can see square root y squared will be y, and y squared to the power of 2 is y to the power of 4. And it is easy to evaluate this integral. Is that right? Can you do that? What is integral y dy? Integral y dy is y squared over 2 minus, that's the minus there, integral y to the power of 4 dy is y to the power of 5 over 5. So that will be pi times y squared over 2 minus y to the power of 5 over 5. And the limit of integration is from 0 to 1. And you know how to find the value of this. Is that right? And that will be pi times, replace your y by 1. 1 over 2 minus 1 over 5. That is the upper limit. Minus, replace y by 0. That will be 0. So you don't need to write that. So that will be pi times 1/2 minus 1 over 5. Simplify that. That will give you 3 pi over 10 is the volume generated by revolving this area about the y-axis. And we used the washer method. I hope you understood the various steps that we took in doing this problem. Alright, now watch how this area is revolved about the y-axis. That's a beautiful animation. Again, I acknowledge this is taken from the same web page I gave you in the last class. Alright, watch it again. That's a beautiful animation of how this area is revolved about the y-axis, generating that beautiful solid. Is that right? Alright, there's another example of how a washer is generated. Actually, this is the complete disk, and this, you can see the R out, the outer radius and the inner radius. Alright. As you can see here, these animations are taken from mathdemos.gcsu, and I would like to acknowledge that at this point. Let's actually look at one more of this animation, and they are very useful. Now look at this. We are revolving this area about the y-axis. The first thing we do is divide this into various dAs and see how each of the area is revolved. I want you to watch that. You can see that's a dV, this is one dV, this is another dV. That's right. Now look at one dV being generated. This is now only done half of it, only the half of the volume that is generated on the other side. That's a beautiful animation. And the total volume is obtained by adding all these dVs. So we found the volume generated on the other side, and now the complete volume is generated. So that's right. Now this is a beautiful animation. Alright, I would like you to access this web page and look at more of these animations. Alright, let's look at that just one more time. How the whole area is divided into dAs, and just one of such dAs is revolved to generate one dV. And there are many such dVs, and you have the total volume added to give the complete volume. All right, let's get out of this and continue with our discussion. Now, let's do a problem. Find the volume generated when the area enclosed by the graphs of f of x equal to square root of x and g of x equal to x squared is revolved about the x-axis. Now, what we did earlier was two functions of y x equal to y squared and x equal to square root of y. The area enclosed by the graphs of those two functions were revolved about the y-axis. This time we have two functions of x, f of x equal to square root of x and g of x equal to x squared is revolved about the x-axis. All right, how does that look? First of all, let's graph these functions. F of x equal to square root of x and g of x equal to x squared. How does f of x equal to square root of x look like? Well, that's the graph of square root of x. How about g of x equal to x squared? That's the one. In fact, you notice that it's the same area as we considered before. So, this is now going to be revolved about the x-axis. All right, what do we do? First of all, find points of intersection so that we get the upper and lower limits. How do you do that? By equating f of x equal to g of x. In other words, square root x equal to x squared. Well, that will give you x equal to 0 and x equal to 1. I don't think you need my help to solve that. X squared equal to square root of x. In fact, if you square them, you get x equal to x to the power of 4. Is that right? Yes. Now take all the quantities to the left side, factor them, and set each factor equal to 0, and you get x equal to 0 and x equal to 1. So this is x equal to 0, and that is x equal to 1. Take a strip area dA of width dx at right angles to the x-axis. Now, in the case of revolution about the y-axis, we took dA at right angles to the y-axis. This time we need revolution about the x-axis, so we take dA at right angles to the x-axis. All right? So what will that be? We will construct an area dA here at right angles to the x-axis. What is the width of that area? The width of that area will be dx. That's right. Okay. Now, revolving this area about the x-axis, what will you generate? If you revolve that about the x-axis, we generate a washer of thickness dx. So this is the washer. If you revolve that area about the x-axis, you generate this washer of thickness dx. That will be the thickness dx there. All right? That will be... Now, the outer radius of the washer, look at this. The outer radius of the washer is this distance, which is f of x. The inner radius is this, which is g of x. So, the uppercase R of x is the same as f of x. I hope you're following this. When you revolve this area about the x-axis, the outer radius is that distance, which is f of x. And the inner radius is the radius of the hole, that is g of x. So, the uppercase R of x, which is the outer radius, is square root of x. And the inner radius, lowercase r of x, is g of x. And therefore, what is the volume of the washer? What is dV? What is the volume of the washer generated? It will be pi times uppercase r squared minus lowercase r squared, that quantity, multiplied by the thickness, which is dx. So that will be dV equal to pi times uppercase r squared minus lowercase r squared dx. And what is uppercase r? uppercase R is this distance f of x equal to square root of x. So this big R is square root of x. When you square it, it will become x. And the lowercase r is x squared. So that will be pi times square root x squared minus x squared all squared, and that quantity times dx. Simplify that. That will be pi times x minus x to the power of 4 dx. And now you can integrate that dv. This is our dv. In order to find the total volume obtained by revolving the whole area about the y-axis, what do? Integrate that dv from x equal to 0 to x equal to 1. So we get v, the total volume, is integral 0 to 1 of dv, which is pi times, you can see that pi is a constant, pi times integral 0 to 1 big R squared minus small r squared, that quantity, times dx. And of course, that is this quantity. That will be pi times integral 0 to 1 x minus x to the power of 4 dx. Integrate that. Integral x dx is x squared over 2 minus integral x to the power of 4 dx is x to the power of 5 over 5, and that multiplied by pi. Alright. Now, find the value of that by using the upper limit minus the lower limit. So that will be pi times, put x equal to 1. 1 over 2 minus 1 over 5, that is the upper limit. Then minus, put the lower limit. I will give you 0, so there is no need to write that. And simplify that, you get 3 pi over 10 is what you get by revolving this area enclosed by f of x equal to square root of x and g of x equal to x squared. The area enclosed by these two graphs when revolved about the x-axis, that is the volume you get. Can you visualize what that volume will look like, what that shape will look like? You need to have that mental picture created. Then only you will enjoy the mathematics of it. Alright, you can see that is being generated there. That is a beautiful shape, is that right? Okay, all these animations are taken from the same web page. It contains a lot of resources. Alright, now let's do another one. Find the volume of the solid generated by revolving the area bounded by the graphs of y equal to 2x squared, y equal to 0, and x equal to 2. A about the y-axis, B about the x-axis, and C about the line y equal to 8, and finally D about the line x equal to 2. So there are 4 parts for this problem. Now to begin with, we need to figure out that area. What is that area enclosed by these graphs? Y equal to 2x squared. Well, let's draw the graphs of this. Now, you do that on your calculator. Y equal to 2x squared, y equal to 0, and x equal to 2. Those are the graphs that generate that area. Now, tell me, what is y equal to 2x squared graph look like? That's right. This is the graph of y equal to 2x squared. Where is y equal to 0? Y equal to 0 is the x-axis. That's right. So this is y equal to 2x squared, this is y equal to 0, and what else? X equal to 2. What is the graph of x equal to 2? There you go. That's x equal to 2. And the area enclosed by these 3 graphs is this area. There you go. Now, First of all, we need to revolve this area about the y-axis and find the volume. Can you figure out if this whole area is revolved about the y-axis, what kind of a solid shape do you generate? Picture that in your mind. Alright, so remember our axis of revolution is the y-axis, and in order to find the volume we of course take an area dA, and always when you take the area dA for the disc and washer, that area dA must be taken at right angles to the axis. So we take a strip of area dA of width dy perpendicular to the y-axis. So here we have that area dA of width dy. Now remember, when you want to revolve about the y-axis, the functions need to be functions of y, because the distances that you measure from the y-axis is called x equal to. The functions given to you are y equal to. So this y equal to 2x squared, you need to write it as x equal to something. Now tell me, y equal to 2x squared, can you express that as a function of y? What do? Solve this for x. And what does that give you? It will be solve for x first, x squared equal to y over 2. Therefore, x equal to plus or minus square root y over 2. We take the positive part. So x equal to square root of y over 2. This function is now f of y. You see, originally we were given f of x equal to 2x squared, and that is the same as f of y equal to square root of y over 2. I hope this skill is something that you have now mastered. You can see this is the graph of y equal to 2x squared. Express that as a function of y by solving from that equation for x. You get x equal to square root y over 2, or f of y equal to square root y over 2. That is this function graph. That means this distance equal to f of y. So this distance equal to f of y. What is this distance? If this is x equal to square root y over 2, then this distance is x equal to 2. Is that right? This line is called x equal to 2. That distance is x equal to 2. So g of y equal to 2. This is the graph of g of y equal to 2. So we have both the functions expressed as functions of y. Alright? Now, where is the point of intersection? You have f of y and g of y meets at this point. In other words, f of y equal to g of y, we need to solve for this. And when you revolve this area, this dA about the y-axis, what we're going to generate is a washer. A washer which has a hole in the middle. That's right. So this is your f of y, in other words, f of y equal to square root y over 2 is actually the radius of the hole. That is this radius. F of y equal to square root y over 2. And what is the outer radius? The outer radius is g of y equal to 2. So we have the outer radius and the inner radius. The uppercase R, and this is the lowercase r. So to find C and D, what do? We solve f of y equal to g of y. F of y equal to g of y. And can you solve and tell me what the value of y is here? Square root y over 2 equal to 2. Square both sides. you get y over 2 equal to 4, or you get y equal to 8. That's right. So this is y equal to 8, and this is y equal to 0. That means the position of this element area can change from y equal to 0 all the way to y equal to 8. That's right. So y equal to 0 is the lower limit, y equal to 8 is the upper limit. Now, when dA is revolved about the y-axis, we generate this washer of outer radius big R, which is 2, is that right? And the inner radius small r, which is your f of y equal to square root of y over 2. So big R equal to 2, that is your outer radius, that distance. That's right. And the inner radius is square root of y over 2 is this. Alright, once you have all this information, it is now simple. Alright, now the volume dV of the washer, can you recall that expression? The volume dV of the washer is pi times big R squared minus small r squared quantity times d by the thickness of that disk. So that would be dV equal to pi times big R squared minus small r squared times dy. This is not supposed to be dx, it's supposed to be dy. It can be dx only when you revolve it about the x-axis. So correct that printing error there. So that will be pi times big R squared is 2, so that will be 2 squared minus small r is square root y over 2. That is square root y over 2 all squared dy. You can see another printing error there. This is 2 over y, it must be y over 2. So that will be pi times 2 squared is 4, square root y over 2 squared is y over 2 times dy. And now we have dV, this is our dV, and in order to find the total volume obtained by revolving this whole area about the y-axis, we integrate dV from y equal to 0 to y equal to 8. And therefore that will be integral 0 to 8 pi times 4 minus y over 2 dy. Pi of course will come out, and you can integrate this quantity now. That'll be pi times integral 4 dy is 4y minus integral y over 2 dy is, what is, you see y over 2 is 1/2 y. That will be 1/2 times integral y dy is y squared over 2. And the two 2's on the denominator will give you a 4 on the denominator. So integral y over 2 dy is y squared over 4. And the lower limit is 0, the upper limit is 8. Again, the lower limit will not give you anything because 0 will make both these 0. We need only the upper limit. That will be pi times 4 times 8 minus 8 squared over 4. That will be 16 pi. That is the volume generated when this area is revolved about the y-axis. Okay, I'm sure you can do that now on your own. If you generate this area about the x-axis, what will be the volume generated? Now, in order to revolve this area about the x-axis, how do we take the element area? The element area that we take must be at right angles to the axis of revolution. So let's do that now. Part B, to revolve this area about the x-axis, we take a strip of area of width dx at right angles to the x-axis. So this time, the area that we take must be at right angles to the x-axis. And what is the length of that? The length of that will be, this is the function y equal to 2x squared. And therefore the length of that will be y equal to 2x squared. That's right. Okay. Now revolving this dA about the x-axis actually generates a disk. This time the area is actually sitting on the x-axis. So we have no washer. This time it is a disk. Will generate a disk of radius r equal to this function, which is 2x squared. So the radius of the disk generated will be 2x squared. That's right. So you generate a disk by revolving that, and the volume and the radius of that will be 2x squared. And the position of this can change from x equal to 0 to what? What is this value? This value is where 2x squared meet x equal to 4. Is that right? This is x equal to 2. This is x equal to 2. This is x equal to 0. So we integrate that volume dV from x equal to 0 to x equal to 2. Alright, first let's obtain volume dV of that disk. What is dV for that disk? Because it is a disk, you don't need to subtract the volume of the hole. The volume dV will be pi times r squared dx. So dV equal to pi r squared dx, where r is this distance, which is equal to 2x squared. So dV equal to pi times 2x squared all squared dx. And that will be 4 pi x to the power 4 dx. That's the dV, the volume of the disk. What do you do now? The dA can be anywhere from x equal to 0 to x equal to 2. So we integrate that dV from x equal to 0 to x equal to 2 to give you the total volume V. V equal to integral 0 to 2 dV, which is 4 pi times, is that right? 4 pi is a constant, so we take it out. Integral 0 to 2 of x to the power 4 dx. And what is integral of x to the power 4 dx? It is x to the power of 5 over 5. So 4 pi times x to the power 5 over 5 from x equal to 0 to x equal to 2. Again, the lower limit is not going to yield you any value, so we need only put the upper limit. That will be 4 pi times 2 to the power of 5 over 5. What is 2 to the power of 5? It's 32, is that right? Yes, so 4 pi times 2 to the power of 5 over 5. Now, you notice a common error that students generally do, which I have done here too. What is that error here? Now, I have actually replaced x by the upper limit. That means I have used the limits already. That means you don't have that limits anymore there. That means this has to go. The limits has been used. So that will be 132 pi over 5 is the answer. Alright. We have now done parts A and B. We revolved this area about the y-axis. We obtained the volume generated. We revolved this area about the x-axis and we obtained this volume. And now we need to revolve this about the line y equal to 8. What is the line y equal to 8? If you notice, these two meet at y equal to 8. So a line y equal to 8 will be that line. We need to revolve this area about that line. That is the C part. Alright, let's go and do that. C This is the line y equal to 8. We need to revolve this area about that line. Can you figure out what that solid will look like? And in order to find the volume of revolution about an axis using either disk or washer method, of course this is going to be a washer, is that right? We take an element area at right angles to the axis of revolution, is that right? So we will take an element area somewhere like this. Okay. To revolve it about the line y equal to 8, take a strip of area dA of width dx perpendicular to the line y equal to 8. So here we have our element area dA, and what is the length of that? The length of that will be y equal to 2x squared. That's right. And the width of that will be dx. Alright, and we revolve this now about the line y equal to 8. So, revolving this dA about the line y equal to 8 generates a washer. Now, it will be something like this, is that right? It will generate a washer with a hole at the center. Now, what is the outer radius? Can you tell me what the outer radius is? Outer radius is this distance. What is that distance? That's y equal to 8. And what is the inner radius? Inner radius is this. And what is that? Okay. You may have trouble figuring that out. Now remember, the distance of the graph of a function from the x-axis is called y. Is that right? Y equal to 2x squared. So this distance is y. And therefore, what is this distance? This is the graph of y equal to 8. That means its distance from the x-axis is y equal to 8. So, this whole distance is y equal to 8. And this distance is y equal to 2x squared. Therefore, what is that distance? One more. Watch my fingers here. The distance between my two fingers here is this, which is y equal to 8. And the distance between my two fingers here is that distance, which is the distance of the graph of y equal to 2x squared from the x-axis, which is y equal to 2x squared. So this distance, therefore, is the total distance minus that, which is 8 minus 2x squared. That is the inner radius. So once again, figure it out well. The outer radius is this, y equal to 8. And the inner radius is this distance, which is 8 minus 2x squared. That's right. Okay. So the outer radius is capital R equal to 8. Okay. The outer radius of this washer is uppercase R equal to 8, which is this. And the inner radius is lowercase r, which is that distance, which is 8, minus that distance, which is 2x squared. So lowercase r is 8 minus 2x squared is that distance. The whole distance is 8. This is 2x squared. So that one is 8 minus 2x squared. And therefore, what is the volume of the washer? The volume of the washer is pi times the quantity big R squared minus small r squared times dx. There you go. And your big R is 8. Your small r is 8 minus 2x squared. Let's replace that. So that will be pi times 8 squared minus the quantity 8 minus 2x squared all squared dx. Now remember, there must be a bracket here, and the dx is common to all this quantity. Alright, and that will be, can you simplify this? Well, I can lead you to it, but you must write down and simplify this on your own. First, simplify this quantity. 8 minus 2x squared, the quantity raised to the power of 2. It will be 8 squared minus 2 times 8 times 2x squared. That will be 32x squared plus the square of this, which is 4x to the power of 4. And you notice that when you expand this 8 squared will cancel with, when you distribute that negative, minus 8 squared, they will go. So the first term that will survive is 2 times 8 times 2x squared, that is 32x squared. It is negative here, multiply with the negative become positive. And plus 4x to the power of 4 times negative is this. So that will be pi times 32x squared minus 4x to the power of 4. Now, if you don't understand it, just go back and do the simplification one more time. Expand this and then distribute that negative sign and see whether you get this. Alright, now this is your dv. To obtain v, we integrate dv from x equal to 0 to x equal to 2. And that will be pi times integral 0 to 2, 32x squared minus 4x to the power of 4 dx. Now integrate it. That will be pi times 32 times integral x squared dx is x cubed over 3 minus 4 times x to the power of 4 dx integrated give you x to the power of 5 over 5. The limits from 0 to 2. Again, the lower limit will not give you any value. Therefore, we only use the upper limit. So replace your x by 2. That will give you pi times 32 times 2 cubed over 3 minus 4 multiplied by 2 to the power of 5 over 5. And calculate that. 2 cubed is 8. 8 times 32 is 256 divided by 3 minus 2 to the power of 5 is 32 times 4 is 128 divided by 5. And simplify that, you get 896 pi over 15 is the volume of the solid generated when this area is revolved about the line y equal to 8. Okay, well there is one more left for us to do, and that is revolve it about the line x equal to 2. Revolve it about this line. This area needs to be revolved about the line x equal to 2. Now tell me, if you revolve this area about the line x equal to 2, will you be generating a disk or a washer? If you notice here, that area is actually in contact with the axis this time. Therefore, we will be generating disk this time. When you take an element area, that element area will be in contact with the axis of revolution. There will be no hole when you revolve it. So we are using disk in this case. Okay. So to revolve it about the line x equal to 2, take a strip area dA of width dy. You can see here the width is dy. Why not dx? The width can be dx only if the area is at right angles to the x-axis. This is now at right angles to the y-axis. So the width is dy. Now, that means you need to represent y equal to 2x squared as a function of y, because this time we are measuring these distances. We need to represent the function as x equal to something. I hope you are now clear with this. We need to represent y equal to 2x squared as a function of y by solving for x. We actually did that earlier when we obtained the volume of revolution about the y-axis. What is that we obtained? X equal to square root of y over 2. Is that right? We did that already. So this distance, this is the distance called x equal to square root of y over 2. The distance of the graph of this function from the y-axis. And what is this distance called? That distance is called x equal to 2. Alright, so f of y, this graph is the graph of f of y equal to square root y over 2. There you got it. And this is your g of y, that is 2. G of y equal to 2. Alright, now what are the limits of integration? This area dA can be anywhere from y equal to 0 to y equal to what? We actually solved this point of intersection. Well, we solved and we got y equal to 8. So this dA can be anywhere from y equal to 0 to y equal to 8. Alright, there you go. So the position dA can be anywhere from y equal to 0 to y equal to 8. Now the distance from the y-axis to any point on this curve we just talked about, the distance of the y-axis to any point on this curve is x equal to square root of y over 2. That distance, x equal to square root y over 2. And the distance from the y-axis to the line x equal to 2 is simply x equal to 2. So that is x equal to 2. And therefore, what is the distance from the curve to the line x equal to 2? What is this distance? What is the length of the element area? The length of the element area is the distance from the curve to the line x equal to 2. And that distance is this whole distance, which is 2, minus this distance, which is x equal to square root y over 2. I hope that is clear. We need to get the length of dA. Length of dA is this whole distance, which is x equal to 2. And minus that distance, which is x equal to square root y over 2. So the distance from the curve, from this curve to the line x equal to 2 is 2 minus square root y over 2, and that is the length of the element area dA. So the length of dA is 2 minus square root y over 2. Alright, there we go. When dA is revolved about the line x equal to 2, we generate a disk. And what is the radius of that disk? The radius of that disk is this distance which we just obtained. This is therefore the radius of the disk generated. So uppercase R, the radius of the disk is 2 minus square root y over 2. Alright, that's the disk that is generated. This is the line x equal to 2. The radius of that disk is 2 minus square root y over 2. Alright, what is the volume dV of the disk generated? What is the volume dV of that disk generated? dV is pi times r squared dy. That will be pi times our r is 2 minus square root y over 2 all squared dy. And you need to simplify this. Can you simplify that? That will be square of 2, that is 4, minus 2 times 2, that is 4, times square root y over 2, that's the middle term, plus the square of this quantity, that is y over 2. So that will be pi times 4 minus 2 times square root 2. You see, when you multiply this, it will be 2 times 2 multiplied by y over square root of 2. When you simplify that, this 2 and the square root of 2 can be simplified and you get 2 root 2. In other words, it is 2 times 2 divided by square root 2, which is 2 root 2 times square root y. Alright, and the last term is plus the square of this, which is y over 2. Well, by this time, this kind of algebraic process must be simple for you. A minus b all squared is a squared minus 2ab. 2 times square root y over square root 2 is 2 square root 2 square root y, plus the square of square root y over 2 is y over 2. And now we can obtain the total volume by integrating this dv from y equal to 0 to y equal to 8. So the total volume is pi times integral 0 to 8 of this quantity. And to integrate this, remember, square root y is the same as y to the power of 1/2. So we need to write it that way. Now, when you integrate, let's integrate each term. Integral 4 dy is 4y minus 2 square root 2 is a constant, and square root of y is y to the power of 1/2. Integral of y to the power of 1/2 dy is y to the power of 1/2 plus 1 over 1/2 plus 1. 1/2 plus 1 is 3 over 2. So it will be 2 root 2 y to the power of 3 over 2 over 3 over 2 plus integral y over 2 dy will be y squared over 2 divided by 2, which is y squared over 4. And the limit from 0 to 8. Again, because each term contains y, when you use the lower limit, they all become 0. So we need only the upper limit. Okay, let's use the upper limit. That will be 4 times 8 minus, look at this 3 over 2. 3 divided by 2, that 2 will go up and multiply with this 2 to give you 4. So that will be 4 square root 2. Replace y by 8, you get 8 to the power of 3 over 2 over 3. Now remember here, 3 divided by 2, that 2 goes up to the numerator, gets multiplied with this 2. That will give me 4 square root 2 over 3. That's what this is. Plus 8 squared over 4. Now tell me, what is 8 to the power of 3 over 2? Well, that will be actually square root of 8 raised to the power of 3. Square root of 8 raised to the power of 3. Or 8 raised to the power of 3 and take the square root of that. That is 8 to the power of 3 over 2. Or you can put it on the calculator. And put this all on your calculator. That will give you 4 times 8, 32, minus 128 over 3, plus 16. And simplify that again. That is 16 pi over 3 is the volume generated when this area is revolved about the line x equal to 2. So actually these 4 parts of the problem give you all the skills you need to solve any problems of this type. And now try this on your own. Find the volume of the solid generated by revolving the region bounded by xy equal to 6. Now you got to read it as, you can take it as x equal to 6 over y, or y equal to 6 over x, and so on. So xy equal to 6, y equal to 2 and x equal to 6 about the line x equal to 6. That is a good exercise. I have actually worked it out for you in the PowerPoint. So check it out if you have some difficulty. But try and draw the graphs of these two functions and identify the area enclosed and try and revolve it where? About the line x equal to 6, and try and set up to obtain the volume generated. All right?